ARM's history involves a fascinating collaboration between Acorn Computers, Apple, and VLSI Technology. In the early 1980s, Acorn Computers, a British company, was tasked with creating a more powerful microprocessor for their upcoming personal computers. Existing processors like the Motorola 68000 and Intel 80286 were either too expensive or underperformed for Acorn's needs. Inspired by the RISC, reduced instruction set computing concept emerging from UC Berkeley, Acorn engineers, particularly Sophie Wilson and Steve Ferber, designed their own processor architecture. In 1985, the first ARM1 prototype was developed, followed by the ARM2, which powered the Acorn Archimedes, the first commercially available ARM-based computer. By the late 1980s, Acorn recognized that the potential of their RISC-based architecture extended far beyond their own product lines, but they lacked the resources to commercialize it on a global scale. This is where Apple enters the picture. Apple was developing a personal digital assistant, PDA, which would later become the Apple Newton. They needed a low-power, high-performance processor for this handheld device, something ARM's RISC design could offer. In 1990, Acorn Computers, Apple, and VLSI Technology, the semiconductor company that manufactured the ARM chips, formed a joint venture called Advanced RISC Machines Ltd. Limited. This marked the transition from Acorn RISC Machine to Advanced RISC Machine. Following the joint venture, ARM Holdings was established as an independent company. It focused solely on designing processor architectures and licensing these designs to other companies, rather than manufacturing the chips themselves. This business model allowed ARM to scale rapidly, as companies like Nokia, Samsung, and Texas Instruments adopted ARM designs for mobile devices. The Apple Newton, released in 1993, became one of the first major consumer products to use an ARM processor, though it wasn't commercially successful. Nevertheless, ARM's low-power design proved ideal for mobile devices, paving the way for widespread adoption in smartphones, tablets, and embedded systems. Over time, ARM Holdings became the dominant force in the mobile and embedded processor markets. The company went public in 1998 on the London Stock Exchange and later on the NASDAQ. In 2016, ARM Holdings was acquired by SoftBank Group for $32 billion. As of 2020, NVIDIA announced plans to acquire ARM, though regulatory hurdles complicated the process. Today, the acronym isn't officially emphasized anymore, as ARM's influence extends far beyond its original RISC roots, covering everything from smartphones to servers to IoT devices. As of early 2025, NVIDIA did not acquire ARM. Their deal faced significant regulatory challenges worldwide, particularly due to concerns over competition and market dominance in the semiconductor industry. Regulatory bodies in the US, UK, EU, and China expressed worries about how the acquisition might affect ARM's neutral licensing model, which is crucial for its widespread adoption across various industries. The acquisition was formally abandoned in February 2022. After that deal fell through, SoftBank announced plans to take ARM public through an initial public offering IPO, which occurred in September 2023 on the NASDAQ. When comparing ARM and x86 architectures, we're essentially looking at two different philosophies in processor design: RISC, reduced instruction set computing for ARM, and CISC, complex instruction set computing for x86. Both have evolved significantly over time, and each has distinct advantages and trade-offs depending on the use case. ISA stands for Instruction Set Architecture, so ARM is RISC-based and has simplified instructions. ARM uses a smaller set of simple instructions that generally execute in a single clock cycle, and fixed-length instructions. Typically, ARM instructions are 32-bit or 16-bit with thumb mode, allowing for efficient decoding and faster execution. And ARM separates memory access from computation, meaning operations are done between registers and separate instructions are used to load and store data to memory. x86, on the other hand, is CISC-based. It supports more complex instructions that can execute multiple low-level operations in one instruction, like loading from memory and performing an arithmetic operation simultaneously. These instructions can range from 1 to 15 bytes, allowing for more flexible programming, but increasing decoding complexity. And x86 allows operations directly on memory without needing to load data into registers first. ARM is designed from the ground up for low power consumption. ARM processors are widely used in mobile devices, IoT, and embedded systems. ARM chips excel in delivering good performance with minimal energy usage, making them ideal for battery-powered devices. With architectures like ARM Cortex-A and ARM Neoverse, ARM processors are scaling into high-performance computing and servers while continuing to maintain that energy efficiency. Now, traditionally, x86 CPUs from Intel and AMD deliver high peak performance, particularly in desktop and server environments where power is less of a constraint. x86 processors benefit from decades of software optimizations and can achieve excellent performance in complex applications. More complex instruction decoding and execution pipelines lead to greater power draw and heat generation with x86. ARM licenses its architecture to manufacturers like Qualcomm, Apple, and Samsung, who then customize it. For example, Apple's M1, M2 chips are based on ARM architecture but heavily optimized in-house. While originally simpler, modern ARM CPUs incorporate advanced features like out-of-order execution, superscalar pipelines, and speculative execution, closing that performance gap with x86. ARM processors often include Trust Zone. This is a hardware-based security feature that creates a secure environment for sensitive operations. A key feature of x86 processors is their backward compatibility with legacy software, meaning code written decades ago can still run on modern CPUs. To support complex instructions, x86 CPUs use microcode translation and complex decoding stages, increasing latency but offering flexibility. And features like Intel VTX and AMD V with x86 provide robust virtualization, which is important for cloud computing and enterprise servers. So nearly 100% of smartphones and a vast majority of IoT and embedded devices use the ARM processors. Like we mentioned with products like the Apple M series and AWS Graviton processors, ARM is becoming more prevalent in laptops, desktops, and cloud infrastructure. Companies can custom tailor ARM designs to their specific needs, like Apple Silicon in MacBooks, which is optimized for macOS. But x86 is still the dominant architecture in PCs as of early 2025, laptops, and data centers as it has been for decades, particularly with the Intel and AMD processors. x86 is still preferred for gaming PCs, workstations, and scientific computing due to optimized software ecosystems and high performance. Also, that legacy software support. Enterprises rely heavily on x86 for its mature ecosystem and compatibility with existing infrastructure. Now, with ARM, you have the Trust Zone that provides a secure enclave for executing sensitive code, isolating it from the main operating system. And this is especially useful in IoT and mobile devices. While ARM is vulnerable to some speculative execution attacks, many ARM designs were initially less impacted compared to x86 due to the differences in the microarchitecture. The complexity of x86 speculative execution made it particularly vulnerable to these theoretical attacks like Spectre and Meltdown and similar side channel attacks. x86 processors now include mitigations like Intel SGX for software guard extensions and AMD SEV for secure encrypted virtualization, but these do often come with performance overhead. While ARM has long been dominant in mobile, like Android, support for desktop and server environments is growing. Linux distributions run well on ARM, and Windows on ARM is maturing. Apple's transition from Intel x86 to ARM-based M1, M2 processors has proven ARM's capabilities in high-performance consumer devices. Decades of software development optimized for x86 mean it's the default architecture for Windows, enterprise applications, and many gaming platforms. The x86 ecosystem is tightly integrated into virtualization platforms like VMware and Hyper-V, and cloud providers like Azure and Google Cloud. You can take a look at this key metrics summary chart. So ARM is leading in power efficiency and is quickly scaling up to challenge x86 in performance critical areas like laptops, desktops, and even servers. Its modular, license-based model allows companies to customize processors for specific applications. x86 continues to dominate in legacy systems, gaming, and enterprise servers, benefiting from decades of software optimization and backwards compatibility. However, challenges like power efficiency and security vulnerabilities from speculative execution are pushing the industry to consider alternatives, while of course, with the advancement of ARM, it will continue to evolve its vulnerabilities as well as its security challenges.